Hello and welcome. I am Eric, and in this video we're going to be going through Debugging 102, the more advanced approaches to debugging in software development. So in this section we'll talk about the conceptual approach to approaching a problem and debugging it. And just to illustrate the process of development, we're going to be doing this live and fumbling our way through it so that you can see the internal processes that I use for approaching and debugging problems. So let's go over the overview really quick. This is what I consider to be kind of a scientific approach to development and debugging. So the first thing that we always want to do is define the problem that we're trying to solve. The better you can define it, the better you can understand the problem and the context in which that problem occurs, the better you are equipped to actually solving that problem. The better you understand the problem and all the stuff that happens around it, the better you can account for external phenomena affecting your problem. After we have rigorously defined our problem, the next thing that you want to do is you want to do your best to define what the correct solutions look like. These are the correct answers that you'll be using to validate your proposed methodology against. I was thinking about different programming applications to use to illustrate this, and the initial idea that I have is creating some sort of an application that writes out all the prime numbers from 0 to 100. So we already know what all those prime numbers are, so if we were going to do step number 2, we might write out a set of all the prime numbers from 0 to 100 and use that as our ground truth data set. Moving on to step number 3, we want to somehow model the problem conceptually. This is when you go to the drawing board and start drawing the diagrams on how you tentatively think the problem behaves. You can use whiteboards for this, you can use pen and paper, or you can use some sort of a computer-assisted drafting tool such as Visio or MS Paint or Adobe Photoshop, whatever you want. For simpler problems, you can also do this in your head. Depending on how much stuff you can retain in memory, this may or may not work well for you. I happen to have the memory of a goldfish, so I have to write things down often. Often it's also useful to use diagrams, either on physical paper or digital diagrams. There's drawbacks and benefits to each one. With digital diagrams, you are constrained to the limitations of the software tools that you're using. So Visio, you'll be fighting the user interface quite often to diagram what you're trying to do. However, that digital diagram can very easily be shared out to lots of people within your organization. If you're using pen and paper, like pen or a pencil and a notepad, you have the ability to free write any type of diagram you want. However, because it's done in pencil and paper, it's much harder to edit, unlike a digital design. So with that freedom comes a cost of the lack of editability. Sure, you can use the eraser, but sometimes you have to copy and paste many pieces of a diagram together or whatever, and that can become difficult. Also, it's much harder to share paper designs and edit them. So you can take a picture and share that with people, but if somebody wants to edit your design, then they have to get a Photoshop application or something and start modifying it. Another way you can model the problem is by having pieces of paper or some other objects and move them around on a table or some other sort of a prop. And this can also help you visualize the way that something works. For newbies who are learning computer science and learning arrays for the first time, an ice cube tray might be a great way to visualize an array, and moving objects around in ice cube trays is a good way to conceptually visualize how something can move around within an array. So once you've built out your model, you want to come up with a conceptual approach of how you solve the problem within that given model. And you'll come out with like a series of steps, or even just some sort of a conceptual idea on your approach to the problem. And the amount of conceptual problem solving that you need to do is going to scale with the complexity of the problem. So if you have a really simple problem, you'll only do this in your head. But if it's a very complicated problem with a lot of moving pieces, then you may either take it into bite-sized pieces and approach each one individually within your head, or you might actually get a lot more rigorous with your definition of the approach to the problem. Some people like to just dive right in and start writing code. However, there's also benefits and drawbacks to each approach there. You could waste a lot of time writing pseudocode that doesn't necessarily work or is going in the wrong direction, and all your work was for nothing. So the concept with the planning approach here is that an ounce of planning is worth a pound of cure. So the more you can plan beforehand to figure out if you're going to paint yourself into a corner, the better it is in the long term. And when you're going through your conceptual methodology, you can also figure out if your methodology is going to yield the answers that you expect within your set of correct answers. So here, in the case of our prime number example, we would see, does our methodology actually yield the prime numbers as we would expect? And if it does, then it sounds like a very promising methodology to implement. Which leads us to the next section, which is the implementation of our conceptual approach on step number 5. Basically here you're translating your conceptual methodology into discrete steps written in code, and this is when you would type it all out and run it through your compiler. After you've written your code, you want to validate the code by running it and see if the output of the code yields the correct answers as you expect. So the first question you always ask is, does the output match your expected answers? And the question is, how do you see the output of your function to validate that it actually does what it's supposed to do? So the next question would be, does the code correctly predict additional data not in your initial correct answer set? So for example, if we were looking at the prime numbers from 0 to 100, could we also use that same methodology to get the prime numbers from 0 to 1,000? You could have a program that writes all the numbers 0 to 100, or excuse me, all the prime numbers 0 to 100, just by simply writing out each number manually, because you pre-calculated it beforehand. Sure, while that works, it's not as robust as other solutions might be. So you could look for all the prime numbers from 0 to 1,000, 0 to 10,000, 0 to 1,000,000, and the amount of additional labor required there would be very minimal compared to manually computing all those numbers. And then another thing you want to look at is, does your debugger correctly step through the data in the program state as you would expect? So that may not necessarily make a lot of sense right now, but that will start to make more sense as we step into our practical application. But basically, you can think of it as like you're going through all the different steps of doing a math problem, and the math problem's solution is relatively straightforward and mechanical. So let's say you're doing some sort of a long division problem with a whole bunch of steps in between. Basically what you're doing is making sure that each step that you're doing in the process of solving that problem is the correct step, and the data that you're doing or the numbers that you're crunching are the correct values as you would expect through the whole entire process of solving that problem. Now, if you have issues with your development or debugging approach, there are some things that you desire in debugging that problem. So the first one that you really want to aim for is reproducibility in your problem. If you can make it happen over and over again consistently, then that problem is reproducible, and that helps it become much easier for you to debug. The second one is determinism in your problem. And this goes hand in hand with reproducibility, but there may be some cases where problems with software engineering are not necessarily deterministic. You might have some sort of random number generator that generates a sequence of random numbers, and when a particular random number comes up, that's only when your problem manifests, and in every other case, everything works just fine. Maybe your random number generator generates the values 0 to 100, and only when you have 0 do you get your divide by 0 error, which throws everything off, and that becomes a little bit more difficult because it's not necessarily deterministic. It's based off of the random number sequences and however that sequence may be generated. Another very valuable tool in your tool belt is going to be the logging and data collection of your application as it's running. So you'll almost always want to generate output logs where you're writing to disk particular events within the sequence of your program's execution and the different values in the program state that you are interested in. And you can look through your log file and figure out where the program started going awry. And based off of that, you can get a better idea on what section you should start looking at. There's going to be a bit of an art to figuring out what to log and what not to log as well. So that needs to be kind of an intentional decision that you make. You'll also be doing some data collection, probably mostly through a debugger when you're stepping through different sections of your application's code. And you'll be looking at the values of a variable and the outputs of different functions, and looking at the values of memory and how those values change as you move through the execution of the application. Once you have all this information, you'll start to be tempted to come up with a hypothesis on what is causing that problem. The first mistake that a lot of people do is they come up with only one hypothesis, assume that it's true, and begin debugging and troubleshooting their problem as if that hypothesis was 100% certainly true. However, ideally, what you want to do is come up with several different hypotheses, and each hypothesis should be falsifiable. And then you go through the list of all your different hypotheses, and you try to falsify and eliminate each one. And the one hypothesis that's remaining that you can't prove is false may be either the correct hypothesis, or it may be poorly formed where it is not actually a falsifiable hypothesis. Another tool in your tool belt will be the isolation of your problem. You may have lots of different components that can affect your problem, lots of data inputs and function feeds and so on and so forth, and they could all contribute to the problem and cause it to happen one way or another. So what you want to do is remove the influence of each of these different sources. So that lets you focus more in on the root cause of the problem and isolate down the factors that contribute to this problem or phenomena happening. And the way that's usually done is by performing A/B tests. If you can turn some functionality on and off and see whether that causes a problem to be fixed or not, then that lets you see whether or not that section is contributing to that problem. Another huge important tool you have in your tool belt, particularly with scientific type of development, is the validation of your approaches and methodology. So let's say, for example, you have some sort of lens distortion code that is modeled after a physical lens, and you're trying to troubleshoot whether or not your implementation of the fisheye 62 model is matching the actual physical lens that you're trying to model. So you might take a picture with the physical lens and look at the output image, and then compare that to the software copy of that same image picture, and see if the images match. Now, that would be how you would validate whether your model matches the physical representation. And based off of that, you can say, yes, this code section is validated and I don't need to troubleshoot it any further, or this code section has not been validated and this may be another source of issues. So the validation step can also be very useful. So let's say that you do not have output that does not match your expected output. Then one of two issues is going to happen. Either A, the implementation of your solution or approach is going to be wrong. The code that you wrote is not correct. In other words, the math that you're doing, the steps that you're doing in that are just completely off. Alternatively, the solution approach that you're using is just a wrong approach in general. So no matter how well you implement the code, if the underlying conceptual approach is wrong, then there's no code in the world that can save you. If this is the case where the implementation of the solution is wrong, then you need to go line by line through your code and look at it against your concept inside of a debugger, and see if the programmed behavior matches your expected behavior. And almost always you'll find some discrepancy between what it's supposed to do and what it's actually doing. And once you find that discrepancy, you fix it, and then you restart the process all over again and see if you get correct data. Alternatively, if the solution approach is just completely wrong and bonkers, then you need to go back to the drawing board and revise and correct your conceptual model or approach. So if we had some sort of an approach for finding random numbers and our approach was completely wrong, maybe we're only looking at every number that's a multiple of 2 and 3 and discarding everything else, then maybe we need to revise that approach. If you don't know how to resolve your conceptual problem, then you need to go and get creative and look for help or inspiration around you. And sometimes this just means that you have to take a 5-minute break and kind of think through the problem or model it out a little bit more, or find these edge cases that you missed. And sometimes the solution will become apparent and obvious to you. Other times you might have to go and collect additional data and do scientific validation and get a better understanding of the problem that you're trying to solve. And this is all going to be a very iterative process where you may not necessarily 100% understand the problem the very first time that you came through and did your initial approach or your initial attempt at solving the problem. Through the action of solving the problem and your initial failure, you get a better understanding of the problem, so that on your second iteration, you have some ideas on what works and what doesn't work, and whether you're going in the right direction or not, and whether to course correct or not. So, to put this into practice, let's try to write an application which finds the prime numbers from 0 to 100. So the first step that we want to do is try to define the problem we're trying to solve. So I'm just going to open up a notepad document, and we're going to just say find the prime numbers from 0 to 100, and that's pretty much it. Most of the time this is just something that you would keep in the back of your head. So the next thing that we want to do is have some valid answers for the set of prime numbers. So we'll say set of correct answers, and I'm just going to use set notation. 0 is a prime number, 1 is a prime number, 2 is a prime number, 3 is a prime number, 4 is not a prime number, so 5 is a prime number, 6 is not a prime number, 7 is a prime number, 8 is not a prime number, 9 is not a prime number, 10 is not a prime number, 11 is a prime number, 12 is not, 13 is a prime number, 14 is not a prime number, 15 is not, 16 is not, 17 is, and we'll just do dot notation. So when I came up with the set of these prime numbers, I'm already coming up with a rough approach for how I'm going to be solving these this problem. So basically, I look at the set of numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, ... And then I ask myself, is this a prime number? How do I know? So 0, that's a given, it's a prime number. 1 is a given, that's also a prime number. 2 is also a given, and that's a prime number. 3, we don't know whether that's a prime number, but we can look at the set of known prime numbers and say, can we get to 3 by multiplying any of the known previous numbers? Excuse me. And the answer is no, we cannot. So we know that 3 is a prime number. The next number is 4. Do we know whether 4 is a prime number or not? Well, we can take these previous numbers, and there's going to be 2 times 2, which is equal to 4, and that combination of multiplied numbers will result in 4, so that is not a prime number, so we remove this from our list of candidates. Now we can ask the same question for 5. Something times something is not equal to 5, so we know that 5 is a prime number. We leave that on the list. Next we have 6. We know that 2 times 3, these two numbers, is equal to 6, and we also know that 3 times 2 is equal to 6, so 6 is not a prime number. 7 is a prime number because we cannot multiply any of these numbers to get 7. 8 is not a prime number because we can multiply 2 times 4. 2 is a prime number, 4 is not, but both of those are values less than 8 that we can use to multiply to get 8, and so on and so forth. And we can do this for every number to figure out whether a number is actually a prime number. And if I recall correctly, this is something called like the sieve or sev, I think it's sieve, of Eratosthenes or something like that. He's some famous dead Greek guy who came up with this 2,000 plus years ago. So already we have a hint on how we're going to approach this problem. And we already have a rough approach on how to do this. So let's kind of attempt to come up with a conceptual approach. Basically, we're going to go from 0 to 100, and actually create a list of numbers then for each number, we want to multiply the set of lower numbers and see if any of them match the current number we're looking at. So if we're looking at the value of 6, we go and look at all the numbers less than 6, multiply them together, and see if we can get to 6. I believe the sieve of Erasthenes, I think that's how it's spelled, he goes through and says, okay, well, I found the value 2, so every even number should be eliminated from the list of contended numbers. And then he goes to 3 and says every multiple of 3 should be eliminated from the list of subsequent numbers. And then he goes to 4, every multiple of 4 should be removed. But because it's already an even number, every multiple of 4 is an even number, so they should already be removed anyway, so we can skip that one. So that kind of gives us a rough idea on our approach. So initially, we know we already need a list of numbers from 0 to 100, and then we need some way to start eliminating or marking numbers within that list to see if they've already been removed. And as we go from 0 to 100 and we mark off multiples of that number as we go up the list, all the numbers that we have left over should be the prime numbers. So let's just conceptually draw this really quick in MS Paint. This is going to be a list of numbers from 0 to 10. Just to, actually, I'm going to do this. And then we'll make this a transparent selection. Perfect. And then double this. Okay, so that's 4 cells. This is 8, and then this is 12, and then we'll just take our numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this is all like super sketchy stuff. Like, we don't need to be perfect in the alignment of anything. We're just considering this kind of like as a throwaway diagram. Once we're done, we will expel it from memory and delete it off of our hard drives and so on and so forth, because it's just super scratch paper type of stuff. All right. And this is going to be the working concept that we use to apply our implementation. So I have Visual Studio here, and we're going to do a function that tries to find random numbers, or excuse me, prime numbers. So let's see, how do we want to do this? We have let's just fumble our way forward. We have a void return type, find primes, and then we'll have an integer which is the highest number that we want to look for, or we'll call it the high end, and we might rename that later on if it makes more sense to do so. And then we'll define the body, void find primes, it's high end. And then the main function should call find primes and 100 is going to be the maximum number that we want to find. And then, let's see, we need our initial list of prime numbers from 0 to 100, and then we're going to start trimming off values from that list. So that gives us a hint that we want an array of some sort. It's going to be an array of integers. Let's see if I remember the syntax. Remaining primes. Maybe the syntax is like this. What's a complaint? Incomplete type is not allowed. I might have to specify something like this. Maybe this needs to be 100. That's going to be a problem, because if this is going to be the high end that we go to, and this is going to be a constant, then I think we might have to go something like this. And okay, so does this need to be a pointer then, because I'm creating a new? Yeah, looks okay. And then we need to have a for loop, and that needs to go up to the high end. Oops, like so. Okay. So now we're counting from 0 to 100, and then now we need to think, okay, 0 is going to be a given. We know that's a prime number. 1 is going to be a given. We know that's a prime number. 2 is going to be a known given. That's a prime number. So maybe we start on 3 instead. Or no, I need to start on 2. A prime number is a number that cannot be multiplied by anything other than 1 and itself. So we start on 2. So now we see, we go through the list of prime numbers, and then we see if it can be multiplied by anything other than, let's see, we have the remaining numbers. So when I actually look at this array, I could also just have an array of Boolean values instead of an array of numbers. And the Boolean values can be a flag for whether or not that array index is a prime number or not. So let's do that. These are just going to be Booleans. And then basically we're going to go from I think a low end. Let's see. B is greater than A, B plus plus. I am totally guessing in the dark here. So we're going to run through our first iteration here and see if we're even close. And then we'll debug our way into a solution. So for B is equal to 0, let's start with 2, actually. Is that right? Oh boy. I'm pretty dumb tonight. Alright. Maybe I'm overcomplicating this already. Maybe I should just leave these as integers for now, and then we can do that as a further optimization later on. So our array of numbers needs to test if it can be multiplied. So let's see. If remaining primes times a is equal, or no, mod a is equal to 0, then it is a divisor. Then we want to remove it from the remaining primes. So this is super hacky and dirty, but we will see in the debugger whether this approach is correct or not. So after we have a list of our remaining primes, we want to loop through the list of primes that are not 0 and print them out. Why do I keep doing that? If remaining primes sub a is not equal to 0, then I want to print that out. Cout. Actually, remaining primes followed by a comma. And then we know that we are going to start at 2, and because we start at 2, we also need to print out zero and 1, and we will create our set operator there and then close our set operator here. Come on, there it is. Okay. I have no idea if any of this is valid. One other issue here is after our function completes, we have a new block of memory that's been allocated in our heap, so we need to delete that. And I don't know if this will actually correctly release the memory, but delete remaining primes. I wonder if I need to do it that way. Does it know how many? Yeah, that looks right. Alright, so the first thing we're going to do is set an initial breakpoint right here. and then we're going to run through our program and look at the data. So if you recall, we are now going to validate our code to see if it yields the correct answers. We don't know if our approach is right or not, so this is going to be the very first iteration. All right, here we go. Let's clear out our watch windows. Let's see, we have our remaining primes, which is about to be allocated. And now remaining primes is, oh, we already see an initial bug. We actually have to put numbers into our remaining primes before we can remove them. So let's do that pre-initialization step. For int a is equal to 0, a is greater than high, and a plus plus, remaining primes sub a is equal to a. Alright, let's run this again. Alright, now we step over this. Remaining primes is allocated. Now we're going to go through our remaining primes array and start assigning values. And as we can see here, remaining primes is starting to be populated. Let's put a watch window, and let's see if I can do an array. Nope. Sub 0, and then 1, and 2, and we can see that this is working as expected. And now as we step through this loop, we should see the remaining primes array being populated. Okay, we can be confident that works. Okay, we'll step through to the next for loop. And now this should have 0 through 100. Now let's go back to our locals, step through this, and let's see if this logic even makes any sense. So remaining primes sub 0 mod, or no, excuse me, a is 2 here. Remaining primes on number 2, this one, mod by 2 is equal to 0. So, we already have a problem, because we are marking off the current value that we're testing against. So now we will rerun this. Okay, so we are on 2, but 2 is equal to 2, so we skip that one. Return, we look at 3, that's not a valid case. Now we should be looking at 4 right here, and we should be setting that to 0, but we are not. Why is that? Okay, this statement here is completely wrong. 4 mod 2 should be 0. So let's get our handy dandy calculator out and double check the math. 4 mod 2 is equal to 0. And 4 is not equal Oh. We need two loops here. Okay. So okay, and A is not equal to B, then remaining primes for B. I believe this is more close to correct. Let's run this again. Okay, so now we have B is equal to A, which is 2. Remaining primes sub B, which is 2. Okay, we'll step through that. That should pass because A and B, which are 2, match each other. Okay, next we're looking at 3. That should pass. Okay, next we are looking at 4, and this should fail. Just to verify, remaining primes sub B is 4, right here. And 4 mod 2 and it should be 0. Okay, and now we're going to say remaining primes sub B is equal to 0. Okay, there we go. Now we have 0 here. But the next thing that we need to do is go back here to our loop and say if remaining primes sub A is equal to 0, then we want to continue, which just means we go up to the very top of the loop and do the next iteration. Because let's say we are looking at 4. We already know that 4 has been eliminated, so we just continue on to 5. Let's restart this and verify that we are correct. Okay, good, good, good. Good, good, good. That's 3, 4. Then 6, we should be eliminating. Yes, correct. So we'll set a breakpoint here and hit the continue button. Now A should be 3. So we went through and we eliminated all of the multiples of 2 from the list of remaining primes. And now we are going to go through and eliminate all the multiples of 3 from the list of primes. So if I did remaining primes, just to double check, sub 6, and then sub 8, let's just do 9. That should be valid still. 10, 11 is valid. Let's do 12. And 12 was eliminated. Let's see, let's do 15 because we know 15 is not an even number, but it is a multiple of 3. Okay, excellent. So it's working as expected, and we're kind of fumbling our way forward, but we're making good progress. Alright, let's step through. Alright, now we're going to start eliminating all the multiples of 3. Let's see if this works. Let's see, B is equal to 3, so we can't eliminate ourselves, so that's good. Let's see, the next one, B is 4, Why are we stepping into this? So we're looking at remaining primes B, which is 4, and that's already a 0. Okay, so we need this line duplicated here so that we skip all subsequent values that we've marked off. Why is this Visual Studio? Oh, come on. While that's running, we have been looping over this process over and over again, validating our collected answers against the generated answers, and we're finding issues, and we're developing our answer generator accordingly. Oh, this is annoying. I think what's happening here is my hard drive is not spinning up very quick right now, and I just hit save, and it's got to spin up on the spindle in order to resume. Come on. This is going to be a terrible video now. How long am I going to have to wait for this? Seriously. I guess I'll have to close it with Task Manager. Oh, it's already open here. Why do I have so many open processes? Alright. I am going to see end task. This is not the kind of troubleshooting and debugging I wanted to illustrate in this video, but bear with me. Why isn't it ending? Oh dear. Here's debug 101. Let's end this one. I think it's having a troubled time ending my task because the disk is not spinning. Let's see, it's running at 100%. How is that possible? Oh, there. Okay, now it stopped. Okay. And it's spiking. Anyway, I could use the same methodology to debug why Visual Studio was hanging there for a bit, but we're just not going to waste time on that. But the idea is that this methodology is generalized, that you can apply it to almost anything. Alright, let's see, where were we? We had copied this line of code here, and we needed to modify this to set to B. Save that. Now we'll continue our debugging. Alright. So step through all this. We'll set a breakpoint for here and then hit continue. And now we should be eliminating all the 3s. Alright. Unfortunately, I might have to copy and paste this all over again. So we're interested in 6. Oops, that's not what I wanted. Let's go with 9. And 15 was also a good candidate. Oops. Okay. Oh, I was clicking too fast. Now I don't know where I am. Okay. B is equal to 5. Remaining primes at 5. That should be a valid value, so we should skip that because it's not a multiple. And now B is equal to 6, but we know that 6 mod, or the value at this location is 0, so we should hit the continue condition, which we do. Excellent. Now we're at 7, and that's not a condition we meet, so we go to 8. 8 is not a multiple of 3, but 8 was also already eliminated by being an even number. Now we go to 9. 9 is still a valid value. We should go into this one. Yes, perfect. Remaining primes, sub 9 is going to be set to 0. And there it is. You can see that just happened right there. And now it looks like we are behaving as expected. So let's assume that is correct and go through. And now it's just a matter of printing them out. So let's look at our console output. 0, 1. And then let's look at our output here. I need another comma right there. Let's fix that really quick just to eliminate confusion. Remove this breakpoint. Run it again. Okay, let's step over to the next line. 0, 1, comma. Okay. And now let's look at our output. Does this make sense? We have our output, and then we also have our text pad with our expected outputs. So we have 0, 1, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, blah, 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 and all the way up to 100. So we have two questions to ask ourselves to validate this output. The first question is, within this set of numbers, do we see any numbers which don't belong here? And just by a cursory glance, it looks like every one of these numbers is indeed a prime number. The second question we should ask is there a number that's missing here that should be here? That would be a little bit more of an exhaustive search, because I would have to go through all 100 prime numbers, but it looks like this is valid. I could probably Google that, but I'm not going to waste my time on that. Alright, so it looks like we have a valid approach for generating prime numbers. So, oh, one other thing I should do is verify that we actually delete this memory as expected. And it looks like we did. An interesting question is, how did it know how much memory to delete? Okay. And now we went and printed off all the prime numbers from 0 to 100. So just to verify that this actually works well, let's increase it to 1000 now. So let's go ahead and run this. And just with the key press of a single button, we increase the number of prime numbers that we can output. And now Visual Studio is hanging again. Let's see if my disk is, oh boy, that's insane. Alright, let's look at our console output. It's taking so long. Alright, I'm going to hit break. Okay, I'm going to try this again. This should be relatively fast, but my CPU or my disk is just taking up a whole bunch of time. I'm not really sure why either. Actually, I have a suspicion that my disk is kind of a low quality disk and is shoddy, and it's kind of like the head on the spindle is having a hard time accessing the data somehow. So if I got a new hard drive, it might fix this issue. That's my initial hypothesis anyway. But why is this taking so long? Our output window is good. Nothing in our call stack, nothing in our output. So this program is currently executing, so I'll set a breakpoint here, set a breakpoint there, and another one there, another one here. And yet, not a single breakpoint is being hit. So there's something else going on here. Okay, let's rerun this. Okay, we hit that line, hit that line, hit that line, hit that line. Okay, let's set a breakpoint there and continue with all the rest. Okay, that looks good. Now we're going to output to the console, and this is when it starts to hang. Now why is it hanging there? It wasn't hanging there earlier, so why now all of a sudden? What's our disk usage? 100% again. Alright, let's set a breakpoint here. Okay, let's continue. Continue. It's not even getting through this line. Okay. Why is my performance always maxed out? Oh, now it's showing 0. Why? Okay, we'll keep an eye on this here. There's nothing it could possibly be reading. Very mysterious. I wonder if it's possible that it's related to me recording a video right now. But that doesn't make any sense. I mean, why would it work if I went from 0 to 100 instead of 0 to 1000? Let's send it back to 0 to 100 and try again. This is now a case of us trying to reproduce an issue that we are currently seeing. So we are right here on this step with our current problem. We have some hypotheses on what could be the issue, and now Visual Studio is freezing. Is it possible that this project needs to be moved off of this hard drive? That would be unfortunate. I know I'm recording to the C drive, so why it's thrashing my E drive makes no sense. C drive is an SSD, this is a hard drive. D drive, these are Western Digitals, this is a Toshiba. Wow, that's really annoying. Anyway, I think we will stop the video here. The general idea is that we have this high-level process for doing debug and development, which we can see here. And we went through a practical exercise and went through this process to fumble our way towards a correct answer. And the last step that we are going to do is run through and see if we can generate prime numbers outside of our initially defined set of correct answers to see if the solution is extensible to bigger domains. I'm going to assume it is because it looked like it was working correctly for the smaller domains, but more rigorous testing would be required before you sign off on this function and say that it's validated. There's other improvements that could also be made to the implementation here. Instead of actually storing numbers, you could just store an array of booleans with the indices of the array being the actual prime number value instead, and that could help you save on memory at the cost of a smidge of complexity, but otherwise okay, now it's about to try to print. And it is still just having a hard time. Alright, well, I hope you guys were able to get a rough idea on debugging and troubleshooting and kind of the high-level processes that you're looking for. Again, to review, if you do have issues that you're trying to debug, you're always going to be looking for reproducibility, determinism in your problem. You'll want to do logging and data collection. In this case, our data collection was through the debugger. If you have a set of hypotheses, you're going to be trying to falsify as many as possible. If you have a whole bunch of contributing factors that could contribute to a problem, you want to focus on isolating each factor to see whether or not it contributes or causes the problem. And this is usually done through A/B tests. And then lastly, you can also have a validation step. Anyway, thank you for watching. This concludes video number 2 in my debugging series. Thanks. Bye.